Okay, so our first video going through our walk through Rudin is a pretty straight. We're going to just go through the example, make sure that we fill in all the holes that sometimes don't seem clear when you're reading a math textbook, especially Rudin. It's very dense and terse. All right, so example 1.1 is we're trying to show there is no rational number p such that p squared equals 2. All right, so a couple of definitions that I'm going to include in here because we need them for our proof. First of all, remember that a rational number, so a rational number is one that can be written as a ratio of integers. M and N are integers. And N is not 0, right? So if you can write a number as a ratio of integers, it is by definition rational. Also, we say a number is even if it can be written as 2 times k, where k is an integer. So any number that can be written as 2 times another integer is an even integer. And it is odd if it can be written as 2 times an integer plus 1. Is an integer. Right? So those are some things that we need in this proof. So we're trying to show there's no rational number p such that p squared is equal to 2, and we're going to do it by way of contradiction. We're going to assume there is a rational number p such that p squared is equal to 2. That's going to be our assumption. All right, so what does that assumption give us? That means that p can be written as a ratio of integers, and we're going to make the condition that m and n share no common factors. Because if they did share common factors, all we would have to do is reduce it and define a new m and n. All right, so this is going to be the reduced form of p. No common factors. All right, so if p squared is equal to 2, p squared is really m squared over n squared if p is equal to m over n, and we're saying that that's equal to 2. This means that m squared is equal to 2 times n squared. Now, also note that if n is an integer, n squared is also an integer. So m squared is equal to 2 times an integer. So remember what that means. This means m squared is even. All right, my claim to you then is that m is also even. And let's see why not, why it is. If m were odd, that is not even, because a number can only be even or odd, or an integer can only be even or odd. If m were odd, then m would be equal to 2k plus 1 for some integer k, and m squared would be 2k plus 1 squared, which is 4k squared plus 2k plus 1, or 2 times 2k squared plus k plus 1, where that is an integer, right? The sum product of integers is an integer. So this means that if m is odd, m squared is odd. And we've already concluded that m squared is even. So m has to also be even. Make sure you understand what we did there. So if m is even, that means m can be written as 2 times k for some integer k. K, an integer. And that means m squared is equal to 4k squared, which is also equal to 2n squared, or n squared is equal to 2k squared. Now, what does this mean? So if k is an integer, k squared is an integer, 2 times k squared is, so n squared is equal to 2 times an integer, and this means n squared is even. And as we saw up here, if n squared is even, this means n is even. Because if it were odd, then n squared would be odd, as we showed up here. Thus, m and n share a common factor, that is 2, which is a contradiction, right? We assumed that we had it in reduced form. Thus, our assumption is bad. And our assumption was that there was a rational number, p, such that p squared is equal to 2. There is no rational number such that p squared equals 2. That's it.